Last time, we learned about two different categories of machine learning algorithms, supervised and unsupervised. We learned about one particular algorithm for unsupervised learning called k-means clustering. Today, we'll be looking at supervised learning. We learned last time that supervised learning algorithms require a supervisor who tells the robot which category each data point is in during the training process. The way this happens is by creating a column in our data table that specifies a label that defines which category the data point is in. Let's see how this works with our example data from last time. Our whole data set looks like this. We, the supervisor, need to put some labels on the data to show the right answer. So let's first decide how we will sort the data. To start out with, let's sort the data by size. So we'll say that the big objects will be category 0 and the little objects will be category 1. So we'll create a new column called label and we'll label the data. Now, in the k-means clustering lab, we really only did the first phase of the learning process, training. Today, we'll do both phases, training and testing. So that means that we can only use some of our data for training, so that we will have some data points left over that the learning algorithm has never seen for the testing phase. Let's keep track of which data points will be used for training and which for testing. A general rule of thumb is that we could use 90% of our data for training and 10% for testing. Now, we don't have very much data in this example problem, so we'll use a bit more than that for testing. We'll pick 2 points from each category to use for testing. We'll keep track of which points we're using for training and which for testing in these next columns. I'm going to pick this point as a testing point for category 1, and I'm also going to pick this point, and then I'll pick this point as a testing point for category 0, and this one is another point for category 0. I didn't pick these points for any particular reason. I just picked them more or less randomly. So we'll identify the rest of the points here for training. If we had lots of time to spend on this, we would randomly pick the testing points and test our learning algorithm, and then we would randomly choose the testing points again so that we had different testing points next time, and then test our learning algorithm again. But since we don't have a lot of time, we only have 1 day to spend on this, we're just going to do all of our tests with this set of training data and this set of testing data. Now, let's look at some of the algorithms that we could use for learning this data. First, we'll learn about 2 different algorithms, support vector machine and artificial neural networks. Then we'll write some code to do these algorithms and we'll do some experiments. Let's start with a method called support vector machine. Let's picture our data as points in 2-dimensional space. Here, I'm going to use color to separate out the points in different classes. So the red points will be in one class and the blue points in another class. Suppose that our data looks like this. Support vector machine is an algorithm that will find a line that separates these 2 classes of data optimally. We define optimally in this way. If we would draw a line between the closest data point in one class and the line found by support vector machine, and then we would draw a line between the closest data point in the other class and the line found by support vector machine, these two distances will be equal. In other words, support vector machine finds a line that separates these two classes in such a way that the distance between the classes and the line is maximized. Also, it finds a line such that these two lines that represent the distances meet the line that separates the two classes at a right angle. Now, I showed this example with data points that are in 2 dimensions. In other words, we only have 2 features that we're measuring from the data points, but support vector machine will work in any number of dimensions. For example, our example problem has 3 dimensions: color, sides, and size. When we use support vector machine on our data, it will find a plane that separates the data in an optimal way. Also, suppose that we had 4 or 5 or 6 or more features from our data. In this case, support vector machine would find a shape that's called a hyperplane, a plane in more than 3 dimensions that separates the data optimally. Now, once support vector machine has found this plane, it can categorize new points that it's never seen before simply by checking which side of the plane the new object falls on. So suppose that it sees a new data point it's never seen before over here. Because this data point falls on this side of the line, it will say that it belongs to the red class. If it sees a data point over here, because it falls on the other side of the plane, it will say that it belongs to the blue class. Support vector machine could also be used to learn more than 2 classes of data by classifying one pair of classes at a time. For example, suppose that we had 3 classes of data represented here by red, blue, and green points. We could use support vector machine first to find a line that optimally separates the red and blue points. Then we could find a line that optimally separates the red and green points. And we find a line that optimally separates the blue and green points. Now, when we see a new point, all we have to do is check to see which side of each of these 3 lines it is on. For example, suppose the point falls on the red side of the red and blue line. Next, we'll check to see whether it falls on the red side or the green side of the line separating red and green. For example, suppose that we see a point over here. First, we'll check to see whether this point falls on the red side or the blue side of the line separating red and blue. If the point falls on the red side, we know that the point is not blue, but we don't yet know whether the point is red or green. Next, we'll check to see if the point falls on the red side or the green side of the line separating red and green. If it falls on the red side, we'll say that the point is red, and if it falls on the green side, we'll say that the line is green. In this way, we can use support vector machine to tell the difference between any number of different classes. Now, there are some things that can cause support vector machine to fail. For example, I've shown data here that has a property that's known as separability. Separability means that it is possible to draw a straight line or a flat plane in between the 2 classes of data. But it's possible to have data that is not separable. For example, suppose our data looked like this. This data is not separable because there's no way to draw a line between the 2 classes of data. Support vector machine tends to not do as well with data that is not separable. Or let's suppose that some of our data has been mislabeled by the supervisor. In this case, we might have a single blue point floating amongst the red points. It may be that all the rest of the data really is separable, but this one mislabeled point is going to cause some confusion in our support vector machine algorithm. So let's take a look at another algorithm that we could use to do supervised learning. This method is called artificial neural networks. Artificial neural networks is a method that was designed to try and do machine learning by imitating the way the brain works. The brain consists of many individual neurons, each of which does a very simple operation. But with many neurons linked together, complex information can be learned and stored. In an artificial neural network, we have artificial neurons that are linked together like this. Each individual artificial neuron does something very simple. It takes the input that comes on each of these lines, multiplies it by a constant called a weight, adds up all of the values that come into it, and then it limits the result to between some minimum and maximum. The function that it uses to limit the output to between some minimum and maximum is a nonlinear function, and that has some important effects on how the artificial neural network works. An artificial neural network is often able to learn nonlinear data or data that is not separable better than support vector machine. Now, designing an artificial neural network is a little bit more difficult than setting up a support vector machine algorithm because there are many decisions that you have to make in designing your neural network. For example, we get to decide how many neurons there are lined up in each of these little columns. And we also get to decide how many columns of neurons there are. Each of these columns is known as a hidden layer of neurons. We could have one hidden layer, or we could have many hidden layers. Now, it's not necessarily true that more hidden layers or more neurons per layer will do a better job learning than fewer hidden layers or fewer neurons. The reason is because if we have too many neurons, the artificial neural network could do something that's called overfitting the data. For example, suppose we have two classes of data that look like this. We can see that probably the best way to separate this data is just by a straight line between them. If we use an artificial neural network to learn this data and we have too many neurons or too many hidden layers, the artificial neural network might decide to classify the data with an overly curvy line that looks like this. This will not do nearly as good a job of classifying data than this straight line. So when you're setting up an artificial neural network, it's important to select the right number of hidden layers and the right number of neurons per layer. But figuring out what is the right number just takes some trial and error to figure it out. Now, there's another issue we have to keep in mind with artificial neural networks compared to support vector machine. With a support vector machine, we only need to show the learning algorithm all of the data one time in order to get the hyperplane which optimally separates the data. But with artificial neural networks, we have to show the network the same data many times. That's because the learning process in an artificial neural network is iterative. Here's how it works. We show the artificial neural network a piece of data, and that piece of data goes through the input, propagates through the network, and comes out as an output indicating which class the artificial neural network thinks that data point belongs to. We then compare that output against the right answer, which we have because this is a supervised learning method. we tell the neural network how far away the classification that it gave is from the correct classification. That amount of error in the classification then goes through a process known as backpropagation, where we change the values of the weights on all of the neural connections in the network. Then we will present the network with the same data point again. That data point will propagate through the network, producing an output. Once again, we'll check how far the output is from the correct answer, and the error will again be backpropagated through the network, changing the weights. The learning process isn't finished until the weights no longer change each time we show the network a particular data point. Because of this, artificial neural networks can be very computationally intensive. Because of this, in the past, we've often been limited to using very small neural networks to try and learn data. However, with advances in computing technology, we've now started using larger artificial neural networks to learn more complex data. There's a particular term referred to as deep learning that means the use of large artificial neural networks to try and learn complex data. Let's write some code to do support vector machine and artificial neural networks, and let's do some experiments to see how well each one works. The first thing we need to do is install a couple of new Python packages. Open a command prompt and let's set the directory to your Python directory. Now, the first thing you need to install is SciPy. Do pip install SciPy like this and hit enter. You'll need to be connected to the internet in order for this to work, and after you hit enter here, wait until the install finishes. Once your install of SciPy has finished, we also want to install scikit-learn. So we'll do pip install scikit-learn. Hit enter and wait for this install to finish. After this second install has finished, close the command prompt and open up Python idle. Create a new file and let's start writing some code. The first thing we'll need to do is import all of the different packages we're going to use. We'll put all of our imports in and then run the code to make sure that our imports all work. So we need to import numpy as np. We'll import matplotlib.pyplot. Then from mpl toolkits.mplot3d import axes 3d. Then from sklearn import SVM, that will be for our support vector machine. From sklearn.neural network import MLP classifier. MLP here stands for multi-layer perceptron. That's a term that means a neural network that has more than one hidden layer, and perceptron is another term that just means a small neural network. Now, before we write any more code, let's run this and make sure it succeeds. If it doesn't succeed, we'll have to fix our installations before we go on. So run this and make sure that in the shell window you don't get any errors. If you don't get any errors here, that's great. We're going to go on and write some code. If you do get some errors here, the first thing you should try is restarting your computer, because we just installed some new Python packages and maybe they weren't detected by idle yet. Let's create some vectors for our training data the labels that we, the supervisor, will place on the training data and the testing data. So in our table of data, we placed a little X in the training data column for every data point that we're going to use for training. I'm going to pull out each of those points and make a vector of those points. And I'll type all of those in. And to save some time here, I'm just going to skip right over to finishing it. So this is all of our training data from the table typed in. Now I'm going to take the labels and I'll put in the label that we have for each one of these points. I have one too many brackets here. There we go. Now I want to create a vector for the testing data. And just like for the training data, I'm just going to pull out of the table each of these points that we've already identified as being the test points. Before we actually start to use our learning algorithms, I want to plot this data to make sure that it's working and all of the data looks correct. So let's create a figure and some axes for the figure. And now let's do a scatter plot. I have to pull out of my training data list all of the X values here in an array. And here's how I'm going to do that. I'm going to go item 0 for item in testing data. That will be the X vector that we're going to plot in this scatter plot. Item 0 is all of the first elements in the training data. So this vector will be 1, 1, 1, and so on, just the first element. Then for the Y vector, I'll copy this, paste that here, and we want this to be item 1. So this vector will be 4, 3, 1, 1, and so on. Then we'll do it again for the Z vector. This will be item 2. Now I'm going to say what color I want this to be plotted in. So I'll go C equals, and I actually want the color to be different for the two different categories. So the way I can do this is by making C equal to labels. Then we'll have a different color every time the label is 0 than the color that it is every time the label is 1. And I'm also going to set the marker. I want this to be little O's for the marker, and I made a mistake here. This isn't supposed to be the testing data. I want to be plotting the training data. So I'm going to go back here and fix this. There we go. And now I want to put some labels on my X, Y, and Z axes. The x-axis will be the color, the y-axis is the number of sides, and the z-axis is the size. And finally, we'll do plt.show. Now let's run this and see what happens. You should get a plot that looks like this. Now note that all of the purple points are the points in one of the two classes, and the yellow points are in the other class. You'll notice that there are some points missing here. There should be 2 purple points missing, and there should be 2 yellow points missing. Those are the points that we've pulled out of the training data and have set aside as testing data. So let's write in some code to do the support vector machine. Under the testing data line, let's create a support vector machine classifier called CLF. We'll set that equal to svm.svc, open and close parentheses. This is a function that sets up a support vector machine for us. Now, our actual support vector machine model will be equal to this CLF.fit, and then we have to give it the training data and the labels. After this line, we've already found the hyperplane that optimally separates the data. So now we want to use that hyperplane to predict the class of the testing data that wasn't used in the training. So we'll do classification is equal to CLF.predict. And this we're going to give the testing data. Then we can look at what class was assigned to each of those testing data points by printing classification. I'd also like to plot the testing data along with some indication of how it was classified. So let's take this line of code here and let's copy it and paste it above. And now I want to plot the testing data. Here, C is not going to be labels, C is going to be classification. And instead of an O, let's put an X. Now let's run this. And it looks like I made a mistake here. I put SLF here instead of CLF. So let's change that to CLF. And now let's try running it again. And it looks like I made another mistake. This is supposed to just say testing data. Let me see if I made that mistake anywhere else. Nope, let's try running it again. First, let's look at the shell window. This output is the classification. It says that the first 2 testing points were classified in class 1, and the second 2 testing points were classified in class 0. That is correct. Those 4 points really do belong to those classes. We can see this more easily if we look at the plot. The X's are the points that are the testing data, and the color indicates which class those points were classified into. So our learning algorithm correctly placed these 2 points in the purple class and these 2 points down here in the yellow class. So in this case, support vector machine did pretty well for us. But of course, we gave it a really easy problem. These data are clearly separable and there's no misclassification. Let's go back to our code, and now let's write some code to do an artificial neural network classification and see if it does equally well. Down here, after our support vector machine is finished, let's create a classifier that uses artificial neural networks. I'll do CLF is equal to MLP classifier, and now we have to give a bunch of settings for the artificial neural network. We'll do solver is equal to LBFGS. Don't worry too much about each of these different settings. If we had a lot more time, we'd learn about all these different settings. Today, we're only going to take a look at the effect of the number of neurons in each layer and the number of layers that we use. So just go ahead and put in these different settings here. We'll start out with having 5 neurons in each layer and only 2 layers. Okay, now that we have the setup for our multi-layer perceptron, we can use it to create a model. And the input that we give this fit, just like with the support vector machine, is the training data and the labels. So once we have the model, we can use it to create a classification. And the points that we want to classify are the testing data, the points that we did not use in the training. And then we want to plot this also, but I'd like to create a different plot for the neural network so that we can compare how the support vector machine works with how the artificial neural network works. So if we go back up to the top here, let's create a second figure to display what's happening with our neural network. I'll change this to Fig 2. And now I'm going to copy all of these lines for creating a scatter plot and everything else and paste them down here. And change these to X2 so that this gets plotted in a different plot. Okay, let's test this code. Click on Run, Run Module. And let's take a look at both of the plots. So figure 1 is showing you the classification by support vector machine. And here you can see that all of the testing points were classified correctly. Figure 2 is showing you how well neural networks did with the classification. It looks like neural networks also classified all of the data points correctly. So now let's do a couple of experiments. Close your figure window. The first test we're going to do is we'll suppose that we had less training data and more testing data. So up here, take the first testing data point and let's cut it and delete that comma there. And let's paste that point here into the testing data. So instead of using this one data point for training, we're going to put it into testing. So we also have to delete one of the labels, the label that belongs to that first training data point that we just pulled out. Now run the code again. Take a look at figure 1. This point over here is the point that we removed from the training data and we placed into the testing data. Since this is figure 1, this is showing us the classification that was done by support vector machine. Support vector machine classified all of the testing points correctly. However, let's take a look at figure 2. Figure 2 shows us that artificial neural networks misclassified the new testing point, and it also misclassified one of the other testing points that it previously had classified correctly. Let's go back into our code here and let's try and make artificial neural networks work better by giving it more neurons. Here, instead of using only 2 layers, let's increase the number of layers to 3 and then run the code again. You might notice when you run this code that it takes a little bit longer this time to actually give you a plot. Let's take a look at the results. Support vector machine still does equally as well. And now neural networks has classified the points correctly. So increasing our number of hidden layers for the neural network has improved its results when we had fewer points for training and more points for testing. Now I'd like you to do an experiment on your own. Here's the experiment I'd like you to do. Change the labels in the training data so that the training data is not separable. Remember, we learned previously that separable means that it's possible to find a plane or a hyperplane or a straight line separating the classes of data. If you change the labels on the data, you can set up data that is not separable. Then I want you to test to see how well support vector machine compared to artificial neural networks classifies the data. Feel free to change the number of neurons in each layer and also the number of hidden layers in the artificial neural networks to try and get the neural network to correctly learn the data.